Okay, we have our situation that we talked about last time, which was when we start out with a card house type structure for our sandy soil that after shaking becomes more dense packing. And what does that mean when that happens, for instance, in a situation where I have a loose sand? In other words, I have the card house type structure, I have water in the voids because the soil is saturated, I have a clay layer up above, and when I put in my earthquake into this situation, what occurs? The soil particles get into a more dense state, which means that the water's got to go someplace, and we create basically a water layer right in through there. And what happens is my clay then is sitting over a water layer, and that doesn't work. So what happens is that the clay can crack up into like blocks, and then I have these I've created basically these cracks in here, and that means that these blocks can then sink. They want to go down, as I said last time. They want to go down. Well, the water's got to go someplace, and as a result, well, where does the water go? It comes out like this. And as I said, this is commonly seen, and I'm going to show you a little video of this taking place. And so let's watch this video of an earthquake in Japan. And so an earthquake is taking place right now, and the people are feeling the earthquake and panicking a little bit because they don't know what to do. They're sort of stuck in the middle of everything. If you look here, you can see the ground shifting. The soil is underneath this area is liquefying, and it's sort of creating you get this movement. If you look closely there at the crack, you can see it's shifting, the ground shifting. It's not a normal seismic wave, earthquake type of shaking because the soil has liquefied down below. And so the ground is shifting slowly, and you can see that they're showing the utility poles, lamp posts, and there's the ground shifting. Some people just keep going about their life and ride around. You can see the cracks sort of opening up now, and there you start to see some water coming up. Dirty water and sandy water coming up, and that's not broken pipes. Some people think, oh, those are broken pipes. No, those are not broken pipes. That is the water from the liquefied soil coming through. You can see it comes up all around there, and more places. All along there again, this is not broken pipes. This is water from the ground coming up. It's nice that they recorded this while she was obviously distressed while she's making this recording. All over the place. Now, after the earthquake is all done, you obviously have water and you have sand because there's sand coming up with that water as well. And let's look at another one. And again, water coming up.
Liquefaction is a major cause of damage to
and somebody's describing this video.
When groundwater is forced to the surface by seismic shaking.
It comes up Sometimes it comes up quite fast.
The surface is turned to mud, which means buildings, roads,
Sometimes
and
the
vehicles
liquefied
can sink
soil
into
is
the
at the
ground.
surface. If that's the case, then you can see that things are going to sink into
Liquefaction is a major problem in earthquake zones, especially where building has occurred on reclaimed land or
And this
landfill.
is simply another graphic of the same thing that I talked about. Something like that. So, okay. I wanted to start a new topic now, and that is weight-volume relationship. So, we are done with soil classification, and now we're going on to the next topic. And I'm going to tell you right now that all of this is about weights and volumes, and that's it. And so in theory, these are very simple problems because you all know how to do weights and volumes. And if you get the weights and volumes of everything that you need to get, then you can solve any problem that I give you. But there's some terminology, there are some equations, and we may, so there's some things that we need to get straight here. So when we look at a soil, we see what we call a soil has solid particles, it has air, and it has water. And that is what we call a soil. It includes all of those things. So this diagram here has, we've got solid particles there, a number of solid particles. On the solid particles, I'm showing in blue some water. So there's some little water sort of attached to the soil particles. And then we also have air, which is in between the particles and in between the water. So again, we have solids, we have air, and we have water. We put all that together and we call that a soil. Now, so in other words, when I say soil, I mean the solids plus water plus air. And when I say the volume of the soil, I mean the volume of all of that. Of all of that, all of them, the solids, the water, and the air. Now, sometimes I'll say soil particles, sometimes I will say solid particles, same thing. Those are the same thing. So the notation we're going to use is the following. We're going to have W is the weight of the soil. That is everything. In other words, solids, air, and water. V is the volume of the soil, which again is the volume of everything. So very simple. W is weight, V is volume, and that means of the entire soil. W sub S is the weight of the solids. V sub S is the volume of the solids. Capital W sub W is weight of the water. Capital V sub W is volume of the water. So pretty straightforward, easy to remember. I'm going to define something called the voids in the air and water. In other words, everything that is not solid is a void. So the air and the water, we call that the void. The voids, void or voids, we call them voids. So V sub V, capital V sub V, is volume of the voids. Capital V sub A is volume of the air. And so the volume of the voids is the volume of the water plus the volume of the air. So let's just go over. We have weights and volumes, very straightforward. W and V, weight of the soil, volume of the soil. W sub S, V sub S, weight of the solids, volume of the solids. W sub W, V sub W, weight of the water, volume of the water. V sub V, volume of the voids, which is the volume of the water plus the volume of the air. So, again, these are what you need to know. I just went through these. So, but just the total volume then is going to be what? It's going to be the volume of the solids plus the volume of the water plus volume of the air, which is the volume of the solids plus the volume of the voids. And the weights, we just went through them. What do we know? The total weight is the weight of the solids with the weight of the water. Why? Because we're saying that the weight of the air is 0. So these are the volumes, these are the weights. Pretty straightforward. If I say that the soil is saturated, that means, so saturated soil means that the water, is that the water fills all the voids. And so the volume of the air is 0. I have 0 air. There's all just water. So the volume of the water is equal to the volume of the voids when the soil is saturated, and therefore the volume is equal to the volume of the solids plus the volume of the water. So you need to know what a saturated soil means. Now we're going to talk about densities. So we're going to talk about the symbols for densities. Again, this is pretty straightforward. Gamma sub S is density of the solids. Gamma sub W is density of the water. Just a gamma is density of the entire soil. And then we're going to introduce some other densities. I'm going to call gamma sub D is the dry density. What does that mean? That means that, well, first of all, I'm going to say all soils have a dry density, whether they are dry or not. What we do is the dry density is if the soil were dry, if all the water were gone, what is the density of that soil? So even if the soil is saturated, we have what we call a dry density, simply because we basically imagine that the water is gone and we get a density from that. We're going to calculate that out. Same thing. We're going to have a saturated density. Even if the soil is not saturated, what we're going to do is we're going to basically do a calculation to, in a sense, sort of pretend or envision that the soil is saturated and come up with a density for that. And then we're going to call something called the buoyant density. And the buoyant density is gamma saturated minus gamma W. Now, what is gamma W? Gamma W, of course, is density of water. Well, density of water, we know what that is. It's 62.4 pounds per cubic foot, or 9.8 kilonewtons per cubic meter. You need to know those numbers. I'm not going to give those to you. So you need to know these, and you're a civil engineer. You pretty much need to know these for the rest of your life, because density of water just comes up in a lot of different problems in your civil engineering career. So you need to know what the density of water is. So we know what it is. We're going to have equations with gamma W, but we know what it is. We just have to pay attention to which units we're using. And I'm only requiring you to know those 2 units. So as I said, all soils have a gamma D and a gamma saturated. And even if they are not dry or saturated. Now, what you don't want to confuse, there's gamma saturated and there's gamma S. These are completely different things. Gamma saturated is the saturated density, the density of the soil if we envision it to be saturated. Gamma S is the density of the solids. Now, what is the density of a solid typically? Now, how do we get that, and what is it? Well, the way to look at that, what do I think about this? In other words, if you look at a sand particle, for instance, is just a tiny rock. A gravel particle is just a small rock. And if you take a rock, for instance, and you throw it into a swimming pool, it sinks to the bottom. Why does it sink to the bottom? Because the density of that rock is greater than the density of the water. Now, the question would be, how much greater is the density of that rock than the density of the water? Well, it ends up that your typical average everyday rock, it's not true for all rocks, but for your average rock, the density of that rock is about 2.7 to 3 times that, the greater, 2.7 to 3 times the density of water. So if you remember from your chemistry class, the meaning of the word specific gravity. Specific gravity, if you remember, is exactly this number that I'm talking about. In other words, the specific gravity for a typical rock is about 2.7. So that just means that it's 2.7 times the density of water. So specific gravity is gamma S over gamma W. Gamma S being the density of the solids, gamma W is the density of water. So you need to know this. This ends up to be an important number. And you need to know the definition of specific gravity because we're going to use that. Straightforward. It's not always 2.7. Sometimes you have to calculate it. Sometimes I will give it to you in a problem. And so in other words, don't use the 2.7 in a quiz or something like that, or a test or exam that I give you, because that's just a ballpark figure, just to give you a feel for that. And then gamma D is the dry density. What is that? Well, that's the weight of the solids divided by the total volume. How do I know that? Because we assume that the weight of water is 0. And again, when I say the volume of our soil, it's the volume of this whole thing. In other words, I take, in this case, it's a rectangle, because I'm including the air, the water, and the solids. Okay, a few more terms here, and that is the symbol E, we call that void ratio. What is that by definition? It's the volume of voids over volume of the solids. Again, you need to know these. S is the degree of saturation. What is that? That's volume of water over volume of the voids. Now, when the soil is saturated, what do I know? Well, I know that the volume of the water equals the volume of the voids, and that means that S is equal to 1 when the soil is saturated. So if I give you a problem that says the soil is saturated, that means that capital S is 1, and again, the volume of the water equals the volume of the voids. Small w is the water content. By definition, the water content is weight of the water over weight of the solids. Again, another term that you need to know. So you need to know all these. Void ratio, degree of saturation, water content. And you need to know these definitions. Now, there are 3 relationships. I'm going to give you these that can be used as shortcut. I'll verify them here in a minute. But and they should, again, be memorized. So I ask you to do some memorization here. Memorize these. They're going to help you. These are shortcuts. They're going to make your life easier. So it's really helpful to know these equations. Well, S times E is equal to G sub S times W, water content. Gamma is equal to gamma D times 1 plus small w, the water content. Gamma is equal to G sub S plus S times E, quantity times gamma W over 1 plus E. Now, this equation leads very quickly to a couple other equations, and that is that if the soil is dry, then S is 0. There's no water, so S is 0. And that means if the soil is dry, we get a gamma D. If S is 0, this equation breaks down to gamma D is equal to G sub S times gamma W, quantity over 1 plus E. If the soil is saturated, then S is equal to 1 in that equation. And we get that gamma saturated is equal to G sub S plus E, quantity times gamma W, all over 1 plus E. Again, you need to memorize all these equations. A little bit of memorization here in this course. There's not much. This is the most that we will get. Okay, let me do a simple problem to begin with and give you an idea of how the type of problem that we're going to solve. says calculate the void ratio and specific gravity for a saturated soil with a total unit weight of 117 pounds per cubic foot and a water content of 41%. Okay, a lot of words there, and that's part of the challenge in some of these problems. And so let's write this out. It says calculate the void ratio. Okay, well that means E is equal to question mark. So this is the solution to the problem, yeah. So it's a good idea for these problems, just write out. It says, and specific gravity, G sub S equals question mark. So those are what we want to find. Then we take them one step at a time. Soil is saturated. What does that tell me? S equals 1.0. Total unit weight of 117 pounds per cubic foot. What does that mean? Total unit weight is gamma, 117 pounds per cubic foot. Water content of 41%. Small w is equal to 0.41. Okay, so how can we solve this? Well, one way to do it, I can use my shortcut equations. If I know those equations, then I'm given S, I've given gamma, I'm given small w. Well, let me look at this equation. S times E is equal to G sub S times W. Well, what do I know in that equation? I know the S, I know the W. I don't know the E or the G sub S. I've got this other equation. Gamma is equal to G sub S plus S times E, gamma W over 1 plus E. Well, what do I know? I know gamma W, I know S. So when I look at these two, and I know gamma, I've been given gamma. So, what do I have? I've got two equations, and my two unknowns are E and G sub S. E and G sub S. So I have two equations, two unknowns I can solve. Very straightforward. I don't have to think about it a whole lot. So, yes, and then basically I've asked you to solve this at home. Notice that we have to use that gamma W is 62.4 pounds per cubic foot. Okay. All right, I'm going to stop there.